Okay, let's go for chapter 24, which is capacitors. Okay, this is the symbol for capacitors. We use the two parallel plates to represent the capacitor. Okay, great. Now, a capacitor or a condenser is a device that stores electric charge and electric energy. Imagine that we have this capacitor, right? And we charge this plate capacitor, right, with a battery of 6 volts. Well, later imagine that we remove the battery and let's measure the voltage, and it's found to be the same. Okay, now what happens, and we have some charge, right? The charge is stored this that way. Later, let's increase the voltage of the battery. The same thing, let's charge the two plates, remove the battery, and let's check the voltage. And it's found to be the same voltage, correct? But the charge is not the same. If we increase the voltage, we increase the charge. In this case, Q1 is larger than Q0. Now, one more time, if we increase the voltage, we increase the charge stored in the capacitor. Means that we can get this relationship, right? Charge is proportional to the voltage. If we increase the voltage, we increase the charge. How do we eliminate this symbol of proportionality? Using a constant. In this case, the constant is C, and this is called the capacitance, right? Times voltage, correct? So we have then the capacitance is equals to, is defined as the charge divided by the voltage. The units for this new quantity, right, again, this is called the capacitance. Capacitance. Okay, in the unit for this quantity is called the farad, right? Farad. So 1 farad then is equals to, 1 farad is equals to, according to this equation, 1 coulomb divided by 1 volt. That's the farad. Okay, now let's try to calculate the capacitance for this parallel plate, but and also for this capacitor, right? Parallel plate capacitor, also for a spherical capacitor, and also for a cylindrical capacitor. Let's do it. Let's do it. Imagine that we have this parallel plate capacitor. Okay, that this is one. Right, this is the two plate capacitor, correct? Imagine this is positive charged, this is negative charged. We know that we have an electric field in between, correct? The electric field. We found the electric field for these two plates before in the previous chapter, and we found that the electric field is equal to sigma divided by epsilon naught. Remember, looking for capacitance. Okay. Also, from here we can see that sigma is charge over area times epsilon naught. Okay, great. Also, remember, looking for capacitance, we need a potential difference. Potential difference is found to be E times D. Now let's use these two quantities on this equation. And what do we have? So capacitance equals to charge. Now from here, let's solve for charge. Right? Charge is equals to, let's play with these two quantities. Are going to be electric field by area epsilon naught. Okay, so do we have this is electric field, area epsilon naught. Divide this is again the charge divided by voltage, right? Voltage. Okay, let's do it. ED. From here we found the capacitance for this capacitor, right? Two parallel plate capacitor. Is equals to area epsilon naught divided by the distance between these two plates. Again, this is the capacitance for two plate capacitor over D. Great. Now, what about if we have two spherical concentric shells? Let's do it. Let's find the capacitance. Okay, great. So we have this spherical white capacitor. Imagine we have these two white shells. Okay, we have this is the first shell, and this is the second shell without radius, right? Okay, perfect. And imagine this is charge and this is charge. Okay, this is gonna be negative charge and positive charge. That's the total charge. Okay, now how we can calculate then the remember looking for capacitance, so we need to find the charge and the voltage. Let's find the voltage between these two shells, the spherical shells. This equals to, according to the formula, right, the electric field and the dot product of electric field in this length. Okay, but because this radio is found that this product, right, this dot product is just equals to this product right here. Okay, from here what do we have? We have that this potential difference equals to the integral of this right quantity. But this electric field is found using the Gaussian surface, right? It's a Gaussian surface, correct? And we can find in it was found before, right? This electric field. Now let's do it. Again, the electric field is found to be correct. The electric field is equals to kq over r squared. Okay, when we plug this value right here, what do we have? Well, the potential difference equals to the integral from this position to this position, correct, of this quantity, kq over r squared dr. Right, now the potential difference equals to negative. Let's do this. The integral is the total charge, correct? 1 over r is negative, correct, from this position to that position. Oops, that position. Okay, now from here we can find that this potential difference is equals to kq times 1 over rb minus 1 over ra. Correct. Now let's substitute this value right here. Then let's find then the capacitance. Okay, let's do it. Where's the eraser? Let's find the capacitance. It's right here. Okay, great. Now let's go then to capacitance. It's equals to the charge divided by this voltage, which is kq, correct, times 1 over r sub b minus 1 over r sub a. The charges cancel. Also remember that k, the Coulomb's constant, is equals to 1 over 4 pi epsilon naught. Now this becomes 4 pi epsilon naught. Also we can work with this fraction right here. What do we have? This is RA, RB divided by R sub B minus R sub A. Correct? And this is gonna be the capacitance for this concentric spheric shells. So it's equals to, again, 4 pi epsilon naught times R sub A, R sub B, correct, divided by RB minus RA. Perfect. Also we have the capacitance for a cylindrical capacitor, correct? For a cylindrical capacitor, right? Imagine this is the cylindrical capacitor. We have two, correct? Imagine the same thing. The same thing before. This is L. Imagine this is R sub A. This is R sub B, right? And this is lambda negative, lambda positive. So we use the same technique as before, and the capacitance is equals to, for this case, 2 pi epsilon naught times L over ln of R sub B over R sub A. This is for a cylinder. Okay, perfect. Now let's go to capacitors in series and capacitors in parallel. Let's do it. Let's do it. For capacitors in series, capacitors right, in series, we can use this design right here, this circuit, okay, in this way, the circuit in this way. This is one capacitor, another capacitor, correct? This is the voltage or potential difference, perfect, and we have another capacitor right here. This is capacitor 1, right, 2, and 3. Also we have charges, right? Charge 1, let's say 2, and charge 3. Okay, positive and negative. Perfect. So this is saying as if we have something like this, these 3 capacitors in series, correct? It goes in this way. This is positive, this is negative, where we connect it to the battery, for example. And then we have also, right, according to this quantity, we have right here charge and capacitance, where they're also involving voltage. So we have a voltage, correct, through these 2 plates. Right? Then it's found from the design that the total voltage is equals to the sum, right, of the voltage for each capacitor. Right, for each capacitor. But the charge is found to be the same. The charge is constant. Okay, charge, the total charge, total is equals to charge on capacitor 1, also equals to the charge in the capacitor 2. Right, capacitor 2 also charge in the capacitor 3. Correct? Perfect. Now, one more time, let's go to this condition, and it's applied, right, the formula for capacitance, right? We were looking for the potential difference, so potential difference is equals to the charge divided by capacitance, correct, from this equation. Now let's apply this condition right here. This is case 1, this is case 1, case 1, this is 2, 2, 2, 3, 3, 3, and so on. So let's do it then. So the total potential difference equals to voltage in capacitor 1, which is equals to Q1 over C1 plus what? The same thing for the next one, and the same thing for the last capacitor. But look, the charge is constant, means that we can factor the charge, right? So factor the charge, okay, we can call it the total times 1 over C1 plus 1 over C2 plus 1 over C3. Now, when we compare all of them, right? So we call this total, it's gonna be total over here too. When we compare these two, actually we don't call this total, we call this the equivalent. From this picture, we can see that the equivalent capacitance in series is equals to 1 over C1 plus 1 over C2 plus 1 over C3, correct? And this is again the capacitance for capacitors in series, 1 over C1 plus 1 over C2 plus 1 over C3. Alright, perfect. Now let's go to capacitors in parallel. Great, capacitors in parallel. Let's do it. Let's do it. Okay, in parallel. Perfect, parallel. Let's do it. Imagine that we have one more circuit, correct? But this is with capacitors in parallel. This is voltage again, capacitor 1, capacitor 2, right? Capacitor 3, and we have charge 1, charge 2, right? And charge 3. Look, this is similar to this capacitor. Look, imagine that we have this circuit. Again, these are in parallel. Imagine. Okay, the same idea. This is this positive negative terminal right here. The same as this circuit. These two are the same. Again, this is capacitor 1, 2, and 3. Okay, from here we can see that the voltage, right? The voltage is the same, right? The total voltage is equals to voltage through capacitor 1 equals to the other voltage, or equals to the voltage to capacitor 3. What happens to the charge? At the beginning, look, this is the total charge. Total. Total is split by charge 1, charge 2, and charge 3. Correct? So the total charge, the total is equals to charge capacitor 1, right, plus charge capacitor 2, charge capacitor 3. Okay, now let's try to find the capacitance, the equivalent capacitance when we are dealing with capacitors in parallel. Okay, great. In this case, we use this equation, right, from here. Let's solve for the charge. Look, charge is equals to capacitance times voltage. Okay, let's do it. So it's equals to, again, this is charge 1, this is capacitance 1, voltage 1, this is 2, 2, 2, and so on. Great. So what do we have? This is C1, right, V1 plus and so on, right? C3, right, delta V3, or our potential difference. Okay, perfect. But in this case, look, we found that the voltage is the same for each capacitor. Then let's factor that voltage is gonna be then that voltage times C1 plus C2 plus C3. The same thing as before, right? Now this is the equivalent capacitance for capacitors in parallel. Okay, let's do it. So this is in series, okay? Now the equivalent capacitance for capacitors in parallel is equals to the sum, right, of all the capacitance. That's our in parallel. Perfect. Now let's do one example. Let's involve these two equations, right? Let's do it. Let's see how we can work with them, man. Let's do it. Imagine that we have this this circuit one more time. Okay, we have right here one capacitor. Now we have these two in parallel, correct? Like this, we have another one right here, correct? Oops, right here, correct? Like this, perfect. Now this is, imagine potential is equals to 48 volts. This is, imagine capacitor 1, correct? And this is equals to 6 microfarad. This is capacitor 2, right? This is 3 microfarad. This is capacitor 3, correct? It's gonna be 1 microfarad. And this is capacitor 4, right? And this is, let's say, 12 microfarad. Okay, let's try to do that. Let's try to find that equivalent capacitance. Again, let's find the equivalent capacitance. Also, let's find the charge in each capacitor. Okay, let's do it. Let's try to reduce this circuit. First, let's work with this capacitors in parallel. Remember, in parallel we add these two capacitors, right? So what do we have then? It stays the same, right? Stays the same. This stays the same too, right here. Now it becomes one, right? One capacitor, and then right, the rest stays the same. One more time. This is capacitor 1. This is the voltage, right? 48 volts. This is 6 microfarad. Now let's find this one. This one is the sum, right? Because this is in parallel. The sum is gonna be 4, right, microfarad, and it stays the same, 12 microfarad. Correct? Perfect. Now these three are in series. When they're in series, what do we have? Well, we have that is gonna be the sum of these 3 capacitance. Okay, let's do it. So it's gonna be equals 1 divided by 6 plus 1 divided by 4 plus 1 divided by 12, correct? Perfect. Now this is gonna be in series. It's equals to 2. Great. So what do we have then? We have finally the equivalent capacitance is equal to 2 microfarad. This is 48 volts. Okay, now from here we can find the total charge. Right, the total charge. The total charge is equals to, using the equation from here, for the capacitance, charge is equals to the equivalent capacitance, correct, times voltage. What is the equivalent? 2 microfarad, correct, times the voltage, 2 times 48 is going to be 96, right? 96 microcoulombs. So this is the total charge. The total charge, right, is equals to, we found already the equivalent, right? The equivalent capacitance. Now this is the total charge. The total charge is going to be 96 microcoulombs. Okay, now but what is the charge on each of these capacitors? Well, let's find it. Let's find it. Let's see. These three. Look, these three are in series. Correct. These three are in series. Means that the charge is the same. So the total charge that we found right there is equals to a charge, right? Capacitor 1 plus charge. Now it's in series, right? Charge capacitor 5 plus what? Charge capacitor 4. Correct. Now look, let's find this two. Number 5, right? We call this 5, right? Capacitance 5, right? Is formed by these two, but let's wait for the moment. Let's look for these two, right? These two are in series, means that they have the same charge as the total charge, correct? So from here we can find then that charge 1 is equals to charge 4 and is equals to 96 microcoulombs. Correct. Now what about the charge on capacitor 2 and capacitor 3? Well, to do that, let's try to find first the potential difference, because they have the same potential. These two have the same potential. And then once we know the potential, we know the capacitance, we can add the charge. Okay, let's do it. Let's do it right here. So we know that in series, the voltage, right, is the sum, right, of all the voltages. We have voltage 1 plus voltage 5 plus voltage, right, 4. It must be equals to what? 48 volts. What should be the voltage through capacitor 1? Well, we can find it, right? Voltage through capacitor 1 is equals to, according to this equation, gonna be charge 1 divided by C1. Correct? And what is that? Charge 1 is, what is charge 1? Well, it's the same, right? The total charge is right here too. 96 is gonna be 96 divided by 6. Gonna be 16, right? 16 volts. 16 volts. What about for case 4? What should be the voltage? Okay, voltage for case 4, the same thing, right? It's charge 4 divided by capacitance 4. And it's equals to charge 4, where is the same we found in 96, where the total NC4 is given, right, which is 12. Correct? So 96 divided by 12 is equals to 8. It's equals to 8. So we have 8 volts. In this case, so this is equals to, okay, 16 volts plus this voltage through capacitor 5, right? Plus 8 volt is equals to 48 volts. From here we can find, correct, that the voltage through these two capacitors, which is the same right here, right, is equals to 48 minus what? 60 minus 8. And this is equals to is equals to 48 minus 16 minus 8. Okay, what is this? Okay, one more time. Okay, 48 minus 16 minus 8 equals to 24, right? is equals to 24 volt. So once we know, right, that the voltage right here and right here is 24, these are in parallel, we can now write the charge. Okay, let's find it. So charge 2 is equals to what? Capacitance 2 times voltage 2. Voltage 2 is the same as voltage 5, right? And this is equals to, well, when we multiply 3 times 24, 3 times 24 is equals to 72. This is 72 microcoulombs. What about, right, the charge on capacitor 3? 3 right here. It's gonna be C3, correct? Times change in voltage 3, but it's the same as this one because they are in parallel. Correct. So what do we have then? It's gonna be 1. This is 1 times, gonna be 24. So equals to 24, right, microcoulombs. And of course, in this way, we find, right, the equivalent capacitance and also the charge for each capacitor. This is a very nice example. Okay, great. Now let's go for the last topic for this chapter. The last topic is gonna be energy stored in a capacitor. Okay, let's find the energy stored in a capacitor. To do that, we use some technique as we did in the previous chapters, right? In the chapter 23. Remember, we used this formula to find the work done in charging a plate, correct? So from here we have that the total work is equals to delta or V times dQ. Perfect. Now, but V is coming from this quantity from the definition for capacitance, and this is equals to the integral of what? Charge, right, divided by C times dQ. Perfect. And this is equals to what? Is equals to the total charge squared divided by 2, correct, 2C, divided by 2C. This is the total work to charge the plate. But also, this total work is the energy stored, right, by the capacitor in this case, right? So the work used to charge the capacitor now is converted into the electric potential energy of the capacitor, of the energy stored by the capacitor. Okay, so this is gonna be the energy stored by the capacitor, right, equals to the total charge squared divided by 2. This is 2 right here, right? 2 times the capacitance. But also, look, if we use this formula from here, so we solve for charge, so it's equals to capacitance times V divided by 2C, which is going to be squared, is equals to C V squared divided by 2. Correct? So this equals to C V squared divided by 2. Also, we can, from this equation, solve for capacitance from here, right? Capacitance, so it's equals to charge squared 2 times capacitance, by capacitance is charge divided by voltage. This equals to what? Charge times V divided by 2. So this is also equals to, right, charge V divided by 2. So different ways how we can represent the energy stored for a capacitor, parallel plate capacitor. Okay, great. Now let's go to the energy density, electric energy density. Let's do it. Imagine that we have this quantity and the energy is stored in the capacitor, right, is equals to charge V over 2, correct? Now using charge from the Gaussian law, right, or gaseous law. This is equal. The charge is equals to electric field. Remember, Capacitors says electric field times the area is equals to total charge divided by epsilon naught. Okay, this is the gaseous law. Okay, now let's solve for the charge. So the charge equals to epsilon naught electric field times the area. Okay, perfect. Also from voltage, remember we have the voltage equals to AV. Okay, perfect. Now let's substitute this value right here. What do we have? We have that this electric potential energy is equals to the charge, which is epsilon naught times electric field times the area divided by 2, correct? Times what? Times electric field times the distance. It's equals to what? The separation between the two plates. And this is equals to the electric constant, right? Times the electric field squared, area times d divided by 2. Okay, but what is this? This is when we're dealing with, remember, two plates right here, or two plates. Imagine two plates like that. H2D. They have the distance, they have this area. Inside where we have the volume. So this product gives us the volume enclosed by these two plates. And then this is equals to, from there, epsilon naught area squared volume divided by 2. Now it's very common to use the density. In this case, if we divide this energy by volume, we have a density. In this case is the electric, right, energy density. We use this U to represent that density is equals to epsilon naught E squared divided by 2. Okay, this is very important when we're dealing with the speed of light, right? Electromagnetic radiation. Again, the density that is convert also this one into, we have the radiation, the electric field, and they have the same form. In this way, the speed of light is calculated using the electric field and the magnetic field. This is for the next chapter. Okay, perfect. And with this, we finish this chapter, part 1, right? We need part 2 to finish the chapter in the next video to conclude, right, with capacitors. Okay, see you in the next video.